topic of this section, which is section 1.6, is very important. It's about something called the phase line. You might subtitle this video, Thinking Qualitatively. Rather than quantitatively. We're going to think about ideas. We will do some calculations, but mostly we're going to focus on ideas. What does a phase line mean? How do you think about it in a qualitative way, meaning you're describing general features about it. It's going to be related to where solutions are increasing, decreasing, or staying constant. Equilibrium solutions are going to be the big, rough features that we look for to help us draw this thing called the phase line. I want to motivate it by showing you something from the CD-ROM. In a number of these programs on the CD-ROM, there's something called a phase space that we are viewing. I brought up the program called Chemical Oscillator in this particular situation. It's got something that we call a phase plane, which is a two-dimensional generalization of a phase line. There are two dependent variables that these axes are labeled with. This axis is labeled with an I minus, I believe that's iodine ion perhaps. And this with ClO2 minus, some kind of chlorine oxygen molecule that has got a charge to it. And what the numbers are indicating is essentially concentration level of these different ions in a chemical reaction. You may have seen this chemical reaction in a chemistry class. You've got this container here that's got these chemicals in it. And what you will see here is that these chemicals oscillate over time. I'm going to pick a point to start with in this phase plane. So I'm just going to randomly pick a point down here and click on it. Three things going on in this picture. Make sure we zoom out enough to see them all at the same time. Right here, you see the imaginary chemical reaction going on, and this may jog your memory if you've ever seen a chemical reaction where the colors change over time. Let's stop and clear it all. That's the chemical reaction that we're modeling here. The concentrations of these ions is oscillating over time. Down here you've got graphs of the individual concentrations of the individual ions versus time. And up in the upper left-hand corner you have this phase plane where you don't explicitly see time. Rather, you see points moving around the phase plane. The particular point that you are at a particular instant in time, say you're at this particular point right here, the coordinates of that point give you the individual ion concentrations for these two different ions at that moment in time. The point of this is to look at long-term behavior. Let me clear these out again and restart it. Are there any patterns in the long-term behavior? And in this case, there is. The oscillations essentially settle down in what you might call a steady state. That's indicated in this phase plane diagram with a curve that connects back on itself. We started down here, and the solution curve in this phase plane ultimately approaches this boulder curve, which is a close approximation of something called a limit cycle that's describing how the solutions behave over the long term. They approach that limit cycle in the long term. And when you've got a phase space, it's easy to see that long-term behavior. That's the benefit of the idea of a phase space. So that's a little introduction to the idea of a phase space. Now we're going to go back and think about this simple case of a phase space called a phase line. You're going to have phase lines for first-order scalar equations. dy dt equals something on the right side. We typically only make phase lines for autonomous equations, though in a sense you could try to make some kind of phase line for non-autonomous equations too, but they are harder to interpret because in a sense the phase line can change over time when we've got a non-autonomous equation. dy dt equals f of y, where y is a scalar. So that's a first order scalar equation, autonomous because we only see y explicitly on the right hand side, no t's. We'd like to take equations like this and draw phase lines for them. Well, what does that really mean? The key is, and this is the thing I'm going to emphasize, is to think qualitatively, meaning think about what the graph of the right-hand side of this differential equation looks like as a function of y. The graph that I'm about to graph here is not a graph of solution curves. It's not a graph of the slope field, though we will get to that point. It's just a graph of the right-hand side of the differential equation as a function of y, labeling y on the horizontal axis. And I'm just going to draw the graph of the function. Let's make it look like this. I haven't put any numbers into this. I'm not saying exactly how high this local maximum point is, or this one. I'm not saying how low that local minimum point is. I am specifying where the graph crosses the horizontal axis, here, 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 and here, although I'm not labeling those with numbers. And I am specifying where the function is positive and negative. I'm going to continue to avoid labeling these points, these y-intercepts with numbers. I'll label them with letters. I'll label them little a, little b, little c, and little d. The important thing to realize is those are the values where the right-hand side of the differential equation is 0. In fact, those values of y, if you think about it, are going to correspond to equilibrium solutions of the differential equation. What I want to do now is I want to take that information together with where this graph is positive and where it's negative and draw a sketch of the slope field. And after I draw a sketch of the slope field, that's going to lead me to drawing a sketch of this thing that I'm calling the phase line. So what would the slope field look like? Well, first we have to label it differently. Think about how we've labeled graphs of slope fields before. We've put y on the vertical axis and t on the horizontal axis. Time is explicitly in this particular graph. Think about equilibrium solutions. Those are constant functions that occur at the values of y that make the right-hand side of the differential equation equal to 0. Based on the graph that I've made over here, this graph of f of y, I know those equilibrium solutions occur at these 4 values of y. Y equals a, y equals b, y equals c, and y equals d. I can see that a is a negative value of y, so down here on this graph, I'm going to put a down here at a negative value of y. I see up here that b, c, and d are positive values of y. B closest to 0, c next, and d furthest away from 0. On this graph, therefore, those 4 values of y are going to correspond to constant functions which solve the differential equation. Those are equilibrium solutions of the differential equation. The slope field along those horizontal lines is going to be horizontal, because for those values of y, the right-hand side is equal to 0. Remember, for our autonomous equations, the slope field is constant along horizontal lines. And along these horizontal lines, therefore, the slope field is constant with a slope of 0. Now think about where this graph is positive and where it's negative. Thinking about what that means in terms of the differential equation, that's going to correspond to telling you where solutions increase and where they decrease. Where the slope marks down here are positive or negative slopes. Let's start with y being less than a. When y is less than a, f of y is negative, meaning when you go down here, look along horizontal lines, constant values of y that are less than a, you're going to have negative slopes. If you're just barely less than a, then f of y is a small negative number, and so down here I've got slope marks with small negative slopes, and I try to make them look as though they've got constant slopes, though it's hard to do perfectly. If I look at y values even smaller, back up here, that means I'm moving further to the left, so f of y is more negative, meaning down in this graph, my slope marks are steeper, a larger negative slope, and that would continue as I go on down. Meaning I've got solution curves that are decreasing for initial conditions down in this regime here. Your solutions are going to look like that. Move upwards. When y is between a and b, up in this graph, f of y is positive. F of y is above the y-axis. Therefore, down here, solution curves have to be increasing. The slope marks have to have positive slopes. And in a similar way, if I'm close to a, there'll be small positive slopes. In fact, if I'm close to b, f of y is close to 0, I'll also have small positive slopes up here close to b. It's in between a and b, maybe about halfway in between, where the slope marks will be steepest, because f of y will have the greatest positive value in there. And that allows you to get a pretty decent sketch of what this slope field is looking like between y equals a and y equals b. Thinking about making solution curves follow these, you'll get solution curves that look like this when the initial conditions are between a and b. Between b and c, careful, it doesn't flip back to decreasing, because though b is a 0 of this function, or root, the graph of the function doesn't cross the axis at b, it just touches it and goes back to positive values, which can happen sometimes. So in fact, down here, you're going to have all positive slopes, both above, directly above and directly below b. And solution curves will be increasing in here too. If you're between c and d, going up here, the graph is negative. So down here, the slope marks have to have negative slope. Something about like this. And your solution curves are decreasing. And finally, when y is bigger than d, looking at the top graph, we see that the function on the right-hand side is positive. So now my slope marks have positive slope, and the slope gets higher and higher as y goes higher and higher. And so your solution curves look like this. They're increasing and in fact concave up. So there we've thought qualitatively. No numbers really, no specific numbers. We're thinking qualitatively about the graph of the function on the right-hand side of the differential equation and what the slope field looks like and what solution curves look like. Now what about this phase line idea? For the phase line, essentially what we want to do is something similar to what I showed you with the phase plane. We want to draw in essentially only the state variable, y, and no t, no time, explicitly in the picture. I'm going to draw a vertical line here. This is supposed to be vertical at least. And think of that as a y-axis. I'm going to mark off points that correspond to equilibrium solutions of the differential equation, horizontal lines in the slope field that are solution curves. But I'm going to only think of them as points on this phase line. And in fact, I'm going to call them equilibrium points rather than equilibrium solutions. And in between these points, I'm going to draw arrows. Upward pointing arrows in regimes where solution curves to the differential equation are increasing, where the slopes are positive. Downward pointing arrows in the places where the y values, those initial conditions, correspond to solutions that are decreasing. And so this is the picture that I get. When you look at this picture, you don't explicitly see t. You don't explicitly see a time. Though you should imagine time elapsing in your head. And in fact, you should imagine this line dynamically in the sense that you imagine points on this line actually moving as time passes. Imagine picking a point, say between D and C, perhaps right there, thinking of that as corresponding to some initial condition for some application perhaps. And then you imagine, because this arrow points downward, that the point moves downward as time passes, corresponding to the fact that the solution curve over here is decreasing down towards a value of c as time goes to infinity. And in fact, you'd have to imagine it slowing down. It never really quite reaches c. It approaches it asymptotically in the limit as t goes to infinity. So you can imagine lots of different initial conditions corresponding to lots of different things that can happen, either increasing or decreasing solutions, or staying constant. If you start at c, for example, you stay constant. Once we've focused on this phase line, we also give names to these equilibrium points based on the type of equilibrium points that they are. If nearby points move away from the equilibrium point, we call it a source, which is what I'm trying to write there if you can't quite see the word. If nearby points move toward the equilibrium point, like they do with C here, we call it a sink. So D is a source, C is a sink. A, think about that, look down here, that's going to be a source. And if you've got a point like B where nearby solutions are both going away and coming toward it, depending on what side of B you are on, you don't call that a sink or a source, you call it a node. So this phase line is a one-dimensional example that we will generalize later on to the idea of a phase plane and even a phase space if we're talking about three-dimensional problems. Very qualitative here. Are we going to do anything quantitative? Well, let's do one quick example of a, well, slightly more quantitative problem at least. What if you encounter this specific differential equation? dy dt equals y cubed minus 3y minus 2. And you are asked to draw the phase line for that differential equation. Well, first of all, one thing that makes this difficult is that I've got a cubic function on the right-hand side. If it were quadratic, we could try to find the roots, which would correspond to equilibrium solutions and therefore equilibrium points, by using the quadratic formula. But I've got a cubic here. Now there is an analog, a much more complicated analog of the quadratic formula for cubics, but most people don't know it. Are you required to know it for this class? No. Let me show you what you should do instead. You could use your graphing calculator, or you could use Mathematica to graph this function. Wrong thing here. Graph this function that's on the right-hand side of the differential equation. With the plot command, y cubed, let's see, it's minus 3y minus 2. Cubics are going to have at least one real root. If you think about the long-term behavior of a cubic, as y goes to either plus or minus infinity, think about that a little bit. You'll realize that cubics do have to have at least one real root. They've got to cross the horizontal axis at least once. What does this one appear to do? Well, it's a little hard to tell here. It definitely, if you can zoom in on that, it's not real bright. There's definitely one root at 2. And in fact, if you test y equals 2, that is a root. 2 cubed is 8, minus 3 times 2 minus 6 is 2, minus another 2 is 0. So in fact, y equals 2 is a root. It's going to give you an equilibrium solution in the slope field and an equilibrium point on the phase line. It's harder to tell whether there's another root there or not. Let's move in closer. I'll plot from -2 to +3. Looks like we might have a root at -1. The graph seems to be perhaps just touching at -1. You really can't say for sure just by looking at the picture whether it just touches at -1 or whether it just barely crosses into positive values just to the right and just to the left of -1. You have to test -1 and see if it really is a root. -1 cubed is -1. Minus 3 times -1 is the same as plus 3. So we'll get -1 plus 3 is +2. Then minus 2 does give you 0. -1 is a root. And in fact, if you factor this polynomial by using Mathematica's built-in factor command, you can confirm that, in fact, -1 is what's called a double root. Can you zoom in and see this very well? This says -2 plus y, or y minus 2. This says 1 plus y squared. 2 is a regular root. Y minus 2 is a factor. -1, in fact, is a double root, a root of multiplicity 2, because you've got 2 factors of y plus 1. So, in fact, those are the only roots of this polynomial. This can be factored as y plus 1 squared times y minus 2. -1 and 2 are the roots, and the graph, as we saw, looks like this. Thinking qualitatively again, I could make a slope field. Let's just jump right to the phase line. Mark off the points that are going to correspond to equilibrium solutions. We now call these equilibrium points. And now think about where the right-hand side, f of y, is positive and where it's negative. It's negative when y is less than -1, and also when y is between -1 and 2, meaning on this phase line you draw downward pointing arrows. Solution curves are decreasing for initial conditions in those places. And when y is bigger than 2, f of y, the right-hand side, is positive, and therefore you're going to get increasing solutions. Draw an upward pointing arrow. This is going to be a source, and this is going to be a node. And that would be the phase line for this equation. That's the basic idea. If you've got a quadratic, use the quadratic formula or try to factor it. Cubic, there are some techniques, but you can also use your calculator or Mathematica. You should also, excuse me, you should also be aware of what to do if you've got other kinds of functions, like, say, sine of y or cosine of y on the right-hand side, you'd have to look at the graphs and use your knowledge about trig functions. For example, the roots of sine of y occur at multiples of pi, integer multiples of pi, to figure out where equilibrium points are and figure out where solutions are increasing and decreasing, and therefore where you get your sources, sinks, and nodes on the phase line. I want to end with a little description about a famous mathematician named Ernst Kummer, a German mathematician who lived, 150 to 200 years ago or so. And he was basically what you might call a number theorist, meaning he thought a lot about numbers. Funny thing about number theorists and many mathematicians in general is that they're not very good at arithmetic, okay? I'm okay. I don't claim to be great at arithmetic, at doing arithmetic in my head. There are, of course, some child prodigies who are very good and maybe end up being mathematicians. But many mathematicians, live in a real abstract realm and are not very good at arithmetic. Well, Kummer was one of those, but he did have to sometimes teach arithmetic to young students. And well, when Kummer encountered simple problems like what's 6 times 4 or what's 8 times 9, sometimes he had to ask his students for the answer. Well, the story goes that one time Kummer was needed to compute 7 times 9 in an arithmetic class or some other class of young students. And Kummer was having a hard time trying to figure it out in his head. And the story goes that his students were, playing tricks on him and didn't want to give him the answer. So what did Kummer do? Well, he did eventually figure out what it was. And here's my idea of perhaps how Kummer figured it out. Kummer realized that, for example, when you multiply things like 7 times 9, you are going to get a bigger answer than, say, 6 times 10. Kummer knew that as you take two numbers and multiply them, but move them closer together in equal amounts, that you get bigger numbers. In a sense, you maximize a product when you move those two numbers together in the limit. 8 times 8, for example, is going to be bigger than 7 times 9, just as 7 times 9 is bigger than 6 times 10, and 6 times 10 is bigger than 5 times 11. So, because of that, Kummer knew the answer had to be bigger than 60. So 7 times 9 is bigger than 60. Kummer also knew that, of course, 9 is less than 10, so this has got to be less than 7 times 10, so the answer's got to be between 60 and 70. Kummer immediately, of course, ruled out even numbers as a possible answer. 62, 64, 66, 68 are ruled out, of course, because being a number theorist, Kummer was very familiar with prime factorizations and knew that all even numbers, of course, have 2 as a prime factor. 7 and 9 don't, so even numbers are out. So that left the odd numbers between 60 and 70. 61, 63, 65, 67, and 69. Kummer, of course, knew that if a number ends in 0 or 5, it's got 5 as a factor, and 7 and 9 don't, so that ruled out 65. Kummer also knew the trick that if you've got a number, say, like 69, and you want to know, is it divisible by 9, for example, it'll be divisible by 9 if and only if, when you add the digits, you get a number divisible by 9. 6 plus 9 is 15. That's not divisible by 9. And Kummer also knew that since 70 was divisible by 7, that 69 couldn't be divisible by 7. Finally, Kummer quickly came to the answer by knowing that 61 and 67 are prime numbers. He was very familiar with prime numbers. So those are ruled out, leaving 63 as the only possible answer. And that was how Kummer, I imagine, probably figured it out, I'm sure in the space of a few seconds, for his class to finally say the answer is 63.